So as you could see from this time lapse, I assembled the cooling system. So what we have, this down here is the cold side of the Peltier cooler, and these two coolers are these Arctic Cooling Freezer 7 Pro CPU coolers with roughly 115-120 watt of TDP. So that's the amount of heat that they can get rid of. Once again, so first we have the cold side heat sink, then we have the Peltier cooler, and then there is a 4x4 centimeter copper plate, and then comes the hot plate of the CPU cooler. And then I use this kind of screws and aluminum plate just to clamp down everything. And now it seems that this is strong enough, so I can hold it like this, and this will not creep in any directions, hopefully. But I think that in the final assembly, when I put it like this, I will put something under the fans or the heat sinks, more precisely, just to support them and get rid of the torque. Because now what the original plan is that this thing will be inside the chamber, inside the cooling box, but there is an issue. So when I hold it like this, I can feel that the weight is pulling down this whole thing. So there is a torque which tries to rotate this thing. So if I just attach this against or to the single layer of polycarbonate corrugated sheet, then the sheet will buckle or bend because of the weight. So I don't know the weight of this, but it feels like it's like 2 kilograms. And then if you try to hold it like this, so that's sort of a lever, and then that rotates because most of the mass is concentrated in this area. So this is just some kind of mechanical issue, let's say. So I will make some kind of support structure which will hold the weight of this. Probably, since there is a big gap here, I will put an aluminum profile there, something like this. So I will try to attach the aluminum profile there and somehow hold it, maybe just some zip ties or something like that. But now, before starting to incorporate this into the box, I will test them in, let's say, dry condition. So I will bring my thermometer here, or a few of them, and attach some here, there, and there, so to different points of this cooling system. And I have my power supply here, or power supplies. So we will try first of all one by one how they work, and then we will try different options. But based on the calculations, we should run this somewhere around 6 amperes, and that will provide us sufficient cooling power. So we will see how this behaves. And just something what I skipped. So I used this foam, which is like a sealing for the Peltier coolers, and you could see that I cut off these edges, which do not belong to the main, let's call it, frame. So then I use those to fill in this gap here. So now there is just a very small area here and there which is like exposed, but it's not a big deal. And what I plan is that everything under this white foam will be inside the box, and everything including this copper plate, which is directly connected to the hot side, that will be outside the box. So we will see how this behaves. But yeah, so let's prepare the power supply and the thermometers and see what this is capable of. So basically we have everything here. So this is the 4-channel digital thermometer. Here are the thermometers, and I use also a K-type thermocouple here, the cooling system, and just one fan because I will just test one side at a time. and therefore I don't want to use two fans. So first let's check this. So I will put this aside somewhere here. This is responsible for measuring the room temperature, and the room temperature right now is 26 degrees. So all the other meters are showing 26, so everything is correct. So then we need a power supply. So I have the cables here, and what I did now is, that is not visible, but my power supply is set to 8 amperes, but it is at 0 watts. So what I will do is I maximize the amps to 8 here, but by increasing the voltage I will allow more and more current to pass through this device. And I will also use a clamp current meter just to show you what are the values. So here we are, and what I do, I want to flip this upside down just for better handling, because we are mostly interested in the top of this, since that's the cold side. So let's start with this side, and what I will do, I just simply attach a thermometer. So I could squeeze this somewhere inside, but I need to deform it a little bit. So one thermometer is attached, and just for fun, for example, to see how the heat is being transferred sideways, let's attach another somewhere here or here. But before you would comment on this, yes, it's not measuring directly. I just cannot squeeze it down directly to the plate, and that's why we have a better thing here. There is a channel in this, so I can just push this in and make it in such a way that it should touch the bottom of the channel, so it will be measuring something which is more related to the Peltier cooler. So this is done. So now we need the fan. So what I do, I just direct it towards the heatsink here. So I put a metal box here so it will not tip over in that direction, and in this direction it's not really allowed because of the cables. So let me attach the power supply. So one clip here to the red and another to the black. So this is all fine, and this is the first startup, so I haven't touched this since I assembled it. So let me just take care of these. It's more nice. And I turn this on. Hopefully it will be at least somewhat visible. 27.8, because I touched it with my hands. So this is over room temperature now, but it doesn't matter. So now I will create some noise by turning on the fan. But hopefully it will be fine. So the problem is, of course, that the fan tries to move. So once again, we will measure the temperature here. This is above the cold side, and this is far away from the cold side, but we are curious about the heat conductivity in this direction, or thermal conductivity. And then there is one K-type thermocouple here in the middle. We will power this first, who knows how much, let's say 1 volt. So I turn on the power supply and just allow 1 volt to run through the cooler. So 1 volt and 0.6 amps. And I measured that as well by just putting it here. Meanwhile, since the temperature is changing, it dropped down, so 0.5 amps. So that's pretty much okay. And I will just use the last thermometer to monitor the temperature of the air on the other side of this thing. So the air exiting the heatsink will be measured. So now here we have 25 degrees Celsius, of course, but this is just a very short time period, so you could not expect too much. But let's crank up the power and see where we are at higher currents. So let's say 5 volts. So now I have 5 volts and 3 amps. So that's like 15 watts of wattage. So that's the power which is running through the Peltier. It's not the cooling power. So now I can measure the power again, or the current, and I can show it to you. And everything which is like related to the room regarding the thermometers is at 26.5, 26.7. This behind the cooler is 26.7, so that's a bit warmer. But by touching the heat sinks, I have no bad experience, so everything is nice. So let's go to 8 volts, just because of my curiosity. So at 8 volts we have roughly 4.4 amps. So let's check it with my multimeter. So 4.3, and you can see that the temperature here is 9 degrees. So that's the surface of the Peltier cooler, or sorry, that's the surface of the heatsink. And first of all, I feel the moisture on the heatsink, and it's cold. It's very cold. So this looks promising. And now, of course, this is still considered as a like semi-closed system, because the only airflow which is here is just the fan created airflow and the airflow created by me talking here and waving my hands. But the contact between the heatsink and the environment is quite poor, which means that the heat which is being pumped from the heatsink to the hot side is quite low. So therefore this can become relatively cold, because QC is low and the DT can go higher. But if I would add the fan here, that would change the temperatures on both sides actually, because first here we add more heat, so the overall temperature of the heatsink would be higher, and also we add more heat, therefore more heat will be pumped to the hot side, so the hot side temperature will also follow this temperature increase, and the temperature of the hot side will also increase. So let's go up. I was thinking to use this around 6 amps, so I increase the voltage until I reach 6 amps, which is 11 volts, and that's very nice, because that was my prediction roughly. So let's measure the current as well. Six-ish, so it's 5.8 at 11 volts. And that's very good, because if you will remember, I will use this 12 volt power supply. So if we are at 12 volt, we are nearly at 6 amps, which is, let's say, our sweet spot. And we almost reached 0 degrees, so we are at 2.6 degrees Celsius on the hot side, on the cold side, sorry. And now it's still okay to touch, but it's definitely warmer at the heat pipes. So just for a last try, let's check the temperature at 12 volts and also the other details. So now the power supply is set to 12 volts exactly, and the current on the power supply is shown as 6.28. So let me measure it here. So that's pretty much the same. So we are happy. So this means that at 12 volts, which is our goal voltage, we can provide 6.2 amps per unit, which is very close to the sweet spot. So we will be very happy about this. And then this is just one side. So what happens here is we just cool this, and we don't cool this part. So I I will also turn off or turn on this when we are using it in the cooling box. So we can expect very nice temperatures. In fact, this digital thermometer now measures 1.5 degrees Celsius, and the K-type thermocouple is measuring 2.1 degrees Celsius. So almost the freezing point. And I believe that in the box we will go below freezing point easily, because we will have 2 units and a closed and insulated environment. And the air exiting here is now 29.7 degrees. And of course the room temperature went up a little bit because the air behind this is being measured, so yeah. And this is 21.7 degrees Celsius. So there is a small thermal heat transfer in this direction. So now what would be interesting for me, just for fun, since I can access to smaller spaces with a K-type thermocouple, I will touch the side of the copper plate, and we will see, or hopefully we will see. Let's put this here. So now what I try is not short any circuits and touch the side of the copper plate. So this is the copper plate between the CPU cooler and the Peltier cooler, or actually just the side of it. So now you can see that this is at 41 degrees at the edge, and here on the cold side heatsink we measured 2 degrees roughly, so that's DT equals 38, and that is almost the DT that I would like to aim for. So we are approaching some numbers that we really want to see. This is very good. And now the power supply's cooling just turned on. So now I'm measuring the back of the copper plate, because you know there is a small gap between the 4x4 centimeter copper plate and the 3x3 centimeter CPU cooler hot plate. Yeah, so this is very promising. So the hot side is, let's say, somewhere between 45, 48, maybe 50 degrees, but that's very good, because then if we use the DT equals 50, then we end up around 0 degrees Celsius on the cold side. So I think this will be more powerful cooler than the previous, for obvious reasons, but still this will be very nice to see.